Sarah, what's up? This is going to be video number 5, I think. We're going to go through the rest of your current packet in chemistry, and in subsequent videos, we'll go back through the older stuff, and then we'll get into the math too, just so you can have common sense explanations of all the stuff that you're dealing with, okay? So first up, we're on page 4 of the new packet, the Bohr's model of the atom, okay? So this Bohr guy, I think he was German, and about 100 years ago, he came up with a model for the hydrogen atom, which was the protons and neutrons are boom in the nucleus, and then electrons orbit around the nucleus like planets orbit around the sun. I think I may have mentioned that in some other videos, but that's kind of what it was. Nowadays, we know that's not exactly true, but back then, it's the best he could do, and it's the best anybody really could do, and it was a reasonable presumption, let's say, and they kind of ran with it. So on your notes, it says he proposed that electrons in the hydrogen atom move in circular orbits around the nucleus, and that each orbit represents a specific amount of energy. So like if you're at this orbit, if you're a close orbit, like a Mercury orbit around the sun, it's going to have low energy and then higher energy moving to like the Venus or the Earth or the Mars or the Jupiter, Saturn, whatever. Further away from the nucleus, the more energy that is needed. Just think about it like this. Electrons should be kind of attracted to the nucleus because there's a lot of protons, a lot of positivity in the nucleus. Electrons are negative. They should attract each other. So to move it away from what it's attracted to requires a great deal of effort or energy. It's got to have a good reason to go far from the nucleus. So there's this equation. It's called Bohr's energy equation for the hydrogen atom orbitals. And it's very nasty looking, but it's also very, very simple. And it's this. I'll write it down for you. E equals negative hc, with the Rydberg constant for hydrogen, 1 over n squared. Okay? Now, n is the number of the orbital it's in, the energy level it's in. 1 is closest to the nucleus, 2 is a little bit further, 3 is a little bit further, 4 is a little bit further, and so on. Okay? Now, all this can be broken down and rewritten as this. So this whole HCRH can be rewritten with this number, and it's worth your while to do it, okay? 2.18 times 10 to the 18th joules. Energy's in joules, makes sense that the joules are there. And then this, again, is just the orbital that the hydrogen is in. So H is Planck's constant, C is the speed of light, RH is Rydberg's constant for hydrogen, so that's Rydberg is R, hydrogen is H. And N is the principal quantum number. Principal quantum number. That language is very important to understand because it just means what orbital are you in, what energy level are you in, okay? So it's very basic idea-wise, but it's also very textbooky when you read it, so you want to be sure about what the N is, okay? And it says, note that the energies calculated are negative. There's a negative in the formula leading things off, right there and right there. As N increases, this fraction right here, if you square N, you get a big number in your denominator. If you divide 1 by something huge, you get very, very small. And when you're multiplying something very small, 10 to the negative 18th, by something else very small, it gets even smaller. So, keep that in mind. Negative energy, getting smaller, becomes higher energy orbitals. Okay? So, 10 to the negative 18th is the most amount of energy something could have. Further away from the nucleus, this gets smaller, okay? So in your practice questions, it says, all right, how much energy must an electron have to reside in hydrogen's first orbital? Just pop in a 1 right there. Do the math, you're done. You're going to get this much energy right here because it's 1 over 1 squared, which is 1. You just get this. What about the second orbital? Well, 2 squared is 4, so you get a quarter of this, okay? And a quarter of 2.18 is like maybe 5.5 times 10 to the negative 19th, which is negative 0.55 times 10 to the 18th. So it's a quarter of that number. You just divide this whole thing by 4. But what of the third energy level or the third orbital? 1/9 of this. So you divide this number by 9. Gets smaller, gets smaller, gets smaller. And then the conceptual part at the end is what happens as n becomes infinitely large. Well, as n gets infinitely large, that means that the electron is moving further and further. It's like in the millionth energy level, the gajillionth energy level. It's moving so far away from the nucleus that it's got almost no more energy at all. It's got no more energy at all. Because 1 over something huge squared is going to be 1 over something really super huge, which is basically 0. And when you multiply 0 by anything, you get basically 0. The energy is going to be super, super, super tiny. And that's what happens mathematically. That's why it makes sense. Okay? Pause the video. We're going to go to the next slice. And see you in a second. Okay, we're back. The 5th page. Last page we said how much energy does an electron have if it's in a certain energy level. Okay, cut and dry. Just plug and chug into that formula and you're good to go. Bohr's formula. Now, it says what if, you're not just going to always have an electron staying in an energy level. Sometimes if it absorbs a bit of energy, it's going to jump up to a higher energy level where n is bigger than 1, and then it's going to lose it and then fall back home, or at least fall back part of the way home. So it's going to maybe from like Jupiter to Earth or Jupiter to Mars rather than Jupiter to Mercury, if that makes sense, using an astronomy analogy. So what we want to do is we want to use this equation right here, the change in energy equation, which is this. When an electron goes from a super high energy level, not the whole way back home, it could be all the way back home, but maybe it's halfway home or a quarter of the way home, okay? We got this. And this is a little different than in a previous video where you always had to make sure that this was positive, okay? Sometimes that's going to be negative, okay? Because this particular formula has your final energy level or your final principal quantum amount here and your initial one here. So it's always final squared, 1 over final squared minus 1 over initial squared. It's like, where do you end? I'm going to put 1 over that and square it. Minus, where do I start? And I'm going to put 1 over that and square that. Okay? So, initial energy level here, final energy level right here. And again, all this junk right there, nastiness, can be replaced by this number from the earlier part of this video, negative 2.18 times 10 to the negative 18th joules. Talking about energy, you better be talking about joules. Okay? So, one of your questions says in your practice, what must the energy of the photon absorbed or emitted when an electron moves from the third to the first orbital in a hydrogen atom? And then it asks, well, okay, is it absorbed or emitted? That's actually conceptually a good thing to answer first, even though it comes second, because if something moves from the third energy level to the first, notice I did that with my hand, it's moving from far to close. That means it's giving off energy because it's going closer to home. So if it's giving off energy, it being the electron, it does so in a photon, so the photon has to be emitted. So hopefully that makes sense. If it didn't, or I was too fast, go ahead and just back up a little bit in the video and listen to it again. It will make sense. I promise you. So then, just in order to calculate it, it says from the third to the first. So it starts initially at the third and it ends at the first. So all I would do here is I take my negative 2.18 times 10 to the negative 18th joules number, and I do this. I pop in. It ends at 1, the final energy level right there, 1 squared. The initial one right here, squared, is 3. Goes from the third level to the first level. Notice this is going to be 1, that's going to be 1/9. So, because, 3 squared is 9, All right. So we get this number. One minus 1/9 is 8/9. I'm just going to multiply by that. It's going to stay negative because this quantity is positive, which makes sense. If you have a negative change in energy, that means energy was lost, it was given off, it's emitted. And that's what we expected conceptually when we first attacked this problem. Okay, that's part A. Part B says, what is the wavelength in nanometers of this energy? And is it visible to the naked eye? Got to do a wavelength equation right here. Got to involve it somehow. Okay, we're back. I took the liberty of writing all this stuff out so you didn't have to watch me just looking down my whiteboard and doing all that stuff. But we need wavelength here. That's what we were asked about. So we have to go back to a different equation because clearly this equation right here doesn't have any wavelength in it. And we need one that does. Yet that still incorporates the energy levels, the third to the first. So guess what we use? We use Rydberg's equation. Okay? It's this one from the other video. Now, we have our energy levels here, and we also have wavelength. So what we're going to do is just replace Rydberg's constant with what it really is. That 1.096776 times 10 to the 7th per meter. And then again, remember, we want this. This is the one where we always want it to be positive because we cannot have a negative wavelength. This guy right here is always positive. This quantity should be positive as well. So again, it's 1 over 1 squared minus 1 over 3 squared. 1 minus 1/9 is 8/9. So I'm just going to multiply this number by 8/9, and then we're good to go. Okay? If I did 1 over 3 squared minus 1 over 1 squared, that would be negative 8/9. That would mean the wavelength is negative. Don't want that to happen. So then once you calculate this number, remember it's not wavelength, it's 1 over wavelength. You just got to divide whatever you get here. Put 1 over that number. That's going to be your wavelength. And then how do we tell if it's visible or not? Well, remember, depending on which framework your teacher uses, 380 to 700, 400 to 700, if it's in there, it's going to be visible. If it's not going to be visible to the naked eye. That's it. So just remember that range gets very important. So you can see this is kind of a more advanced two-step problem because we needed to solve for wavelength. Yet you're thinking maybe, I don't know, what do I know that has wavelength and energy? Oh yeah, the Rydberg equation. Okay, and then what is the frequency of the energy? That's part C. Well, we just solved for wavelength. Probably we should use an equation that has frequency and wavelength in it. And wouldn't you know it, it's the most basic one that you even learned last year. It's going to be that. Okay? 3 times 10 to the 8th equals what we just got up here in this equation times the frequency, so we can divide both sides by lambda, and we end up with the frequency equals speed of light divided by whatever the heck we just got in part B. Okay? Plug and chug city. That's all we need to do. Now, if you're paying special attention and you're starting to get, because I'm not sure, again, how comfortable you are with this stuff yet, you might be thinking, hey, I thought there was an energy equation that used frequency, and you'd be right. You can also do this guy, the Planck-Einstein equation, and you would, in theory, get the same answer. Maybe you should try it and see if you do. Okay? Either way is fine. You'd use the energy from part A and Planck's constant, 6.626 times 10 to the negative 34th, and solve for this. Or you could just go here using what you got from part B and the speed of light, 3 times 10 to the 8th. Either way, you should be able to solve for frequency. So, you got some options. The problem usually comes in when in practice, like when you guys are first learning it, your teacher's giving all these worksheets out. It seems like it's 3 separate problems. Okay, part A, part B, part C, but it's all like the same information starting. okay? So rather than saying problem number 1, problem number 2, problem number 3, it's all part of the same problem. They might, on a test or a quiz, just give you all this information at first, like, oh yeah, it jumps from the third to the first. And then they might say, okay, what's the frequency? They might ask just one question about it, and it's part C. So it's implied that you got to solve, hey, how much energy did it take to drop from the third level to the first level? And what is the wavelength of that light that's emitted? And is it emitted or absorbed? We talked about it being emitted. So you might have to do all 3 of these individual problems, although the first 2 may not be listed. It's implied. And why they do that is to see, hey, Sarah, do you have enough comfort with this yet where you can see, hey, if I need frequency, that means I need wavelength, if you're going to use C equals wavelength times frequency. And if I have wavelength, or if I need wavelength, that means I'm going to need the energy, which I get from the Rydberg equation. So there's like a lot of potential for sneakiness going on here, which is why you want to be comfortable with these equations and what's involved in each equation. Okay, what given information is in there? What is each, or what are the variables in each equation? What do they have? So hopefully that makes sense. Again, you have the ability to rewatch some of these, and you can always text me, hey Zach, like, what did you mean by when you were blabbing out about this? So I'm going to pause the video real quick. We're going to go do the last page. Okay, we're back. I think the first video, because I'm still tired. I don't even know what day it is, what time it is. I'm over here in Armenia. I'm leaving tomorrow for Dubai. I don't even know what time zone it is. It's going to be nutty. But I believe we talked about the wave particle duality. That sounds familiar. So that's the de Broglie equation. Lambda equals h over mv. We talked about that. I think that was video number 2 or 3. I think it was video number 3. So go back and check it out if you want to get more and more comfortable with that. The last thing is Heisenberg's uncertainty equation. Now the background on Heisenberg's uncertainty equation is, remember, Bohr said, hey, electrons, they orbit the nucleus of a hydrogen atom like planets around the sun. And that was shown to be not exactly true. This Austrian chemist, physicist, his name was Werner Heisenberg. I think it was Austrian. He's either Austrian or German. What he did, though, is he said it can't. The electrons can't orbit just around the electrons, because the analogy I use with Bryn is, it's like a helicopter's rotating blades. Okay, if you look at them, you can see that they're there. And you know instinctually that they're rotating just really, really fast, but sometimes it kind of looks like a plus sign. When you look up at the helicopter and you just see them spinning that fast, it's almost like a plus sign, and it kind of rotates. Even though you know they're spinning so fast, it's like the optical illusion. It just looks like they're kind of going like that almost. If you don't know what I mean, maybe watch a video on YouTube about just like, oh, here's a helicopter's blades moving, and you'll see what I mean. Okay, but even if you don't know what I mean, imagine you're looking at a helicopter's blades. It's flying up over you. Let's pretend it's like it's watching a car chase in LA, and it's just hovering there, blades spinning so fast. In that disk of rotation, you don't know exactly where the blades are at any one point, but you might be able to tell how fast they're spinning. Or you might be able to like blink your eyes really fast or take a picture of it, and you'll see exactly where the blades are. Okay, you'll see exactly, it'll look like it's just chilling in the air, not moving, but it's because it's a picture. Okay, if you take a picture of a helicopter's rotating blades, you'll see where those blades are, but because it's a still picture, you won't know how fast they're going. So almost it's like for a helicopter's blades, you can know how fast they're going, or you can know exactly where the blades are at in their disk of revolution, but you can't know both at the same time. And that is, well, I won't say exactly, but that's kind of my best approach to explaining the uncertainty equation in the Heisenberg's uncertainty principle for electron location and speed. Best I could do. Hopefully that makes sense. So basically, electrons orbiting a nucleus have the same kind of quality about them. We can't know exactly where they are, but we can know how fast they're going. Or we can know exactly where they are, but we can't know how fast they're going. So we can know one or the other, but not both at the same time. So that's why it's called an uncertainty equation, because we are uncertain about something at all times. We can't know its position, and we can't know its momentum. Now, momentum from physics, as I'm sure you remember, mass times velocity, so that's where the velocity comes in. You can't know where it's at or what its speed really is what it means. But sometimes they'll say momentum and position. The fancy textbook way of saying it. All right? So, the formula for that is this. The change in x, its position, is at least Planck's constant divided by 4 pi, and the change in momentum. That's what m delta v is, the change in momentum. Okay? So it's inversely related to momentum. Position and velocity are inversely related in this relationship. Okay? So, as mass, this is the first question that's asked, where basically m is the mass of an object, 4 is the number 4, pi is the number pi, h is Planck's constant, and v is velocity. Okay? And the change in v, delta v, is the uncertainty in its velocity. And delta x is the uncertainty in position. So, as mass decreases, you can think of this purely mathematically. If m gets smaller, that means your denominator gets smaller. That means the fraction gets bigger, and because the fraction is related to x, it means x gets bigger. Okay? Think of it mathematically like that. You'll get these conceptual questions right every time. It says as the mass of an object decreases, what happens to its uncertainty of its position? Mass goes down. This has to go up. So the smaller something is, the harder it is to know exactly where it is. Okay? Electrons are super small. It's tough to know where they are. Helicopter blades are pretty big. You can you still don't know exactly where they are, but you have a way better idea of where they are than where an electron is orbiting around a nucleus. Cool? So it says practice. Calculate the uncertainty in the position of an electron moving at a speed of 3 plus or minus 0.01 times 10 to the 5th meters per second. And they tell you that the mass of an electron is 9.11 times 10 to the negative 31st kilograms. Okay, again, here's the given info. It says calculate the uncertainty in the position of an electron moving that fast with a little bit of error right there. That's some uncertainty, by the way, because it's either within like 1/100th of this. Okay? But it's uncertainty because we don't know. That's why there's a plus or minus. And its mass is guaranteed to be that. Okay? So, all we need to know is we're calculating this. It said calculate the uncertainty in position. Position is not velocity. Position is x. So, we need to calculate delta x. Well, we already know h. That's Planck's constant. 6.626 times 10 to the negative 34th. We know what 4 is. We know what pi is. We know what the mass is. They give it to us. The change in velocity, most common mistake. People use the whole thing for velocity. We don't care about the velocity. We care about the uncertainty, the delta v, the uncertain part of the velocity, which is this. Okay? 0.01. Now, the second error the second most common error people make is they'll say, aha, I know it's the uncertainty of the velocity. I'll just do this and then I'm done, the 0.01. Because all this stuff is still times 10 to the 5th. So, the delta V you want to use is 0.01 times 10 to the 5th meters per second. Okay? Or basically anything that comes after the plus minus. That's all it is. And then it's just a plug and chug problem. Okay? So you can plug it into your calculator, get an answer. That's all you got to do. Part 2 says calculate the uncertainty and position of an 8,830 kilogram airplane moving at the same speed. Okay, now we just change the mass from this tiny number to 8830. And you can see what happens. If the mass is big, this should get small. Try it on your own, see what happens. That's the newest stuff. Like I said, next video we'll get to the older stuff to catch you up, but I wanted you to at least have this current stuff to kind of catch you up, because if you understand the current stuff, sometimes going back is easier because it's incorporating some of the stuff that you'll have learned like 2 or 3 weeks ago. And then when you look back, you're like, oh wait, this is like, I've already done this in the newer stuff. Rather than just, hey, going with the back stuff, like the back, like 2-3 weeks ago stuff, it may feel like you're always trying to catch up, play catch up, play catch up, play catch up. So maybe this will like stop that, and it will help you not only learn the new stuff, but it kind of incorporates the old stuff anyway. So maybe it'll hasten your catching up process. Anyway, that's my hope. That's my goal. That's my desire for you. Hope you're feeling better. Again, let me know that you have watched this the full way through. I'm going to give you a secret word, okay? Just text me this word and I will know that you have watched this video the whole way through, okay? It's boring, which hopefully this video was not, okay? Hopefully none of my videos are boring, but that's the word I want you to text me, either on regular text or WhatsApp. As soon as you see the end of this particular video, text me boring. That way I will know that you have seen it, all right? Feel better. Next time I give you a video, it will be from the United Arab Emirates in Dubai. Feel better. Have a good weekend. And if you're taking the test on Friday, hopefully this helps. Okay? Text me if you have any questions.